Back with section 5.2 and 5.3 with applications of exponential and logarithmic functions. This one is not quite as spicy as 5.1, but is the last one that we need to do before we get into the real personal finance section, which is chapter 6. So, kicking us off here, our purpose for this is we will solve problems that can be modeled by exponential and logarithmic functions. There are no new notes, so we're going to go ahead and get started with example 1. So a company finds that its daily sales begin to fall after the end of every advertising campaign. And the decline is such that the number of sales is represented by that equation, where X is the number of days after the sale ends. And so it doesn't tell us to put this one in GeoGebra, everyone, but I'm going to anyway, just to kind of get a picture of what the graph is doing and what the sales are doing, so we can dialogue that a little bit. And we'll see, again, I'm going to hold shift, and that's how I'm going to be able to grab and drag these axes. We can see that in this case, this is not going up like our money examples last time, it is going down. And so exponential functions can either have exponential growth, like they did in the one in the lesson prior to this one, or they can have exponential decay, which this is decaying, it is getting to be less. And would eventually reach 0. And if you pull this out forever, it will never go below 0. Just an interesting fact. With regard to exponential functions, this green line here is never going to cross over the line of 0. It's just going to get infinitely close to it as we follow it out. So we are asked, how many sales will be made 10 days after the end of the campaign? So it looks like 2,000 sales were made at the beginning of the campaign. 10 days later, it's going to be about 1,000. It looks like it's going to be pretty darn close to that. And how they don't want to drop below 350 sales per day. So how many days can they let it go without paying for an advertisement? And so this company is trying to save some money and not pay for advertising. And they're wondering, when are we going to drop below 350, which is about right there. So I would guess that that's going to be about 25 days. We will use Wolfram to get the exact answer, but again, GeoGebra, to get just kind of an idea of what's happening here, is a useful tool. So I'm going to slam that in Wolfram exactly as it is. And we need to know 10 days after the campaign. So I got to replace X with 10. Remember, we do need to put a multiplication symbol there. And I think our guess was 1,000. And yes, indeed, after 10 days, the number of sales has dropped to 1,000 per day. So just doing the math really quick for example 1, the way we did that is we had S, which is total sales, is equal to 2,000 times 2 to the power of negative 0.1x. You'll notice that the exponent here is negative, which is what's making it be exponential decay. In terms of your personal finances, you never want to see a negative exponent up there. That would be super bad. And so we will have S equals 2,000 times 2 to the negative 0.1 times 10. In Wolfram is what we put, and we ended up with S equals 1,000. So after 10 days, the number of sales has dropped to 1,000 sales per day. So we were also asked if the company wants to not drop below 350 sales per day, what do they need to do in order to pull that off? So we're going to replace the 10 with the X. We're going to bring that back. And we're going to have 350 as our total sales. And so it looks like the real solution is 25.14, and we're not going to have a 0.14 of a day. So we're going to say that to not drop below 350 sales per day, the company cannot go over 25 days without advertising. So to stay above And you can't see what I'm writing here. 350 sales per day. The company must not go without a sales campaign for more than, was it 24 days? 25 days. And so this company is trying to save as much money as possible by not running sales campaigns, but still keeping their sales up. And so we have cracked the code for them in regard to both of those problems.